Hi there, welcome back. Welcome to Lecture 2. We continue our review today with a few different topics. So the first one is we're going to look at many different types of functions. So we're going to look at rational functions, exponential functions, radical functions. We're also going to talk about their domain and range. And also we'll review the unit circle. So that is a key concept from trigonometry. So you'll need to know all the basic unit circle measures, what the values of sine, cosine, and tangent are at those basic measures. And then last, we're going to solve a few trig equations using our knowledge of the unit circle. Okay, so first, let's review functions. So a function describes the relationship let's say A. Let's erase this and put describes a relationship where every input has exactly one output. And typically, we call this the domain of the function. This is the domain. And then the outputs are called the range. Usually, you denote a function by writing f of x. So in this class, you'll see it usually like this. So f of x denotes a function. X is what you're, I guess, essentially plugging into the function. These are the inputs here. And we'll describe our function using an equation. So this is going to be x minus 2 over x minus 1. We say that this is a rational function. So this is a particular type of function. We know it's rational because it is a polynomial divided by another polynomial. So a rational just means you have like a ratio of two polynomials. Let's talk about the domain and range of this. So the domain of this function is all allowable x values. So basically anything you're allowed to plug into this function, there's only one value you're not allowed to plug in. So we cannot evaluate f of x at x equals 1. That's the only value you can't, because remember, you can't divide by 0. So we would say the domain here is the set of all numbers, all real numbers, where we exclude 1. So the way you write that in interval notation is you have negative infinity to 1, then you jump over 1, and you don't include it by using the parenthesis, and then you do union 1 to infinity. Let's look at finding the domain of another function. So let's find the domain of a radical function. These come up a lot, so I should give you an example of this. Let's do of radical x squared minus 5. We're going to call that g of x. This looks like a minus right here. OK, so for this particular type of function, there is a restriction. What can you not take the square root of? What types of numbers? So for example, if I do some scratch work over here, let's just say this is my scratch work. We know the square root of 4 is 2, because 2 times 2 is 4. The square root of 0 is 0, because it's 0 times 0. However, square root of a negative number, there is no number you can multiply, no real number you can multiply by itself to get this negative 1. So as far as real numbers are concerned, this isn't real. This is no solution. So we need to make sure that whatever is inside the radical is at least 0. So we need basically just copy what's in the radical, whatever it is. So that's what's in the radical this time. you need this to be at least 0. And you have to figure out what are all the values that cause that to be true. Well, we did inequalities in the last lecture, so we know that we're going to find a set of values that make this true. I'm going to start by factoring, and I'm going to get x minus 5. And if you recall, last time we worked on interval testing, so we found those x values where the sign would switch from positive to negative. So for here, that would be where x is equal to 0. And the only other one is right around 5. This factor right here will switch from a positive to a negative. So we need to test 3 different intervals. And how we did that last time was we grabbed a representative from each one. So choose an easy one, make your life easy. Pick like -1 for this one. An easy number here might be 1, and an easy number here might be 6. So what I'd like to do is I'd like to make sure that this is true right here. So that's what I'm testing. And let me grab a different color here. We'll do all the testing in pink. So we're going to test x equals -1. So let's see if this is true. So if I plug in -1, I'm going to get -1 squared minus 5 times -1. This is going to be 1 plus 5 is 6, which is actually bigger than 0. So we know this interval right here works. If you find it easier, you could even test it in the line below. So this one right here, you could test right here. So if I were to plug in 1 into the second line, I'm going to get 1 times 1 minus 5 is -4. That is less than or equal to 0. So that's not true. This is actually just strictly less than 0. This is not true. And it's going to turn out, if I just kind of glance at it, this last interval is also true. It turns out that if all of the powers of your factors, so you see x is to the first power, x minus 5 is to the first power, if all of them are to the first power, it's going to have this alternating pattern like this, where it's like good interval, bad interval, good interval, and it keeps alternating. So you really only need to check the first one, and then you just alternate the rest. If that didn't make sense, don't worry about it. You can still check every single one of them. How do you write the solution here for the domain? So you need everything on this left interval. So that's everything from -infinity to 0. I'm going to leave this a mystery. Oh, I'm actually too low, aren't I? Let me scoot that up a bit. Sorry about that. We'll do it right over here. So the domain is going to be from -infinity to 0, union. And then we start again. We skip the middle interval. We'll start at 5. It'll be from 5 to infinity. You're never going to include infinity. You can't quite get there. So you're going to put parentheses around any type of infinity you ever use. Am I going to include 0? Well, check. So if you go over here, is 0 bigger than or equal to 0? And it is. So you're going to include it. And if you plug in 5, you're going to get another 0. 0 is bigger than or equal to 0. Notice it all depended on the fact that we had this right here. We had an equal to sign. So you're allowed to include these two numbers here. All right, so this is the domain of that radical function. Next, we're going to look at definitions of increasing and decreasing, and also look at some more ways you can put functions together. All right, so let's look at a few more different types of functions here. So go ahead and copy down these two functions. We have f of x is x squared minus 2. So this is just a polynomial. And this is also just a polynomial. It's actually a linear equation because the power is 1 there. We covered that last time. Let's look at ways to put functions together. So I'm going to show you a couple ways. So one way you could do that is you could take f times g. And this is how you notate it. You have fg, nothing in the middle here. It just means multiplication. So what this means is you take this function and you multiply it by this function. So this is equal to f of x times g of x. And what is this times this? It is x squared minus 2 times 2x. And if you wanted to and be fancy, you can just distribute it like this. So you'll get 2x cubed minus 4x. What is the domain of a function like that? Well, it's all real numbers. So I'll use this, this double bar r here to represent all real numbers. That means I can plug in any real number I want. For polynomials, you will always have all real numbers for your domain. How about if I do something like this? So here I'm going to take f, I'm going to divide it by g. So this is equal to f of x divided by g of x. So then I'm going to put f of x on top, g of x on the bottom. What's the domain of something like this? Well, now we have a problem. There's one number that you're not allowed to plug in. And what number is that? It's 0. So you could say x is not equal to 0. That doesn't really describe the whole domain, though. What I like to do is give the interval notation where I jump over 0. I jump over the value I don't need. So you can also add together and subtract functions. It's as you'd expect. I just wanted to show you these two examples. Next, let's look at a definition of a quality of a function. So let's say a function is increasing, and we'll say respectively or decreasing. You can just kind of flip this definition around. Respectively decreasing on some interval, on an interval I, if, so the first one's going to be for increasing. So the first one will be if x1 is less than x2, then the function at x1 is less than the function at f2. We're going to say x1 and x2 are in the interval, so they're in I. I'll just put that over here. So this is what it means to be strictly increasing. That if you give me an x value on the left side of the graph is actually lower over there. And I'll draw a picture of a graph in a second so you can see what I mean. If I flip it around here, so I'm going to say if you're on the left side, if you pick an x value on the left side, that means that f of x1 is greater than f of x2. And this one is for decreasing. Let's look at an example of a graph and see if we can kind of apply what's going on here. So I'm going to kill two birds with one stone and introduce another type of function. So let's say f of x is equal to 1 plus e to the x. Can you see that? You can kind of see that. That's e to the x. I'll try to write lower from there. This is an exponential function. So this is exponential. So it's another important type of function that you're going to need to know how to deal with in calculus. Let's graph this. It's good to remember what the graph looks like. And if you're not sure what the general shape is, just off the top of your head, it might be a good idea to make a table. So I'm going to go ahead and make an x and a 1 plus e to the x column. So these, you consider these my y values. I'm going to plug in easy to work with x values. Don't pick anything crazy. I'm going to start with, I'm going to pick -1, I'm going to pick 0, I'm going to pick 1. Pick maybe a negative value, pick maybe a positive value, so you can get a nice spread of what's going on. If you plug in 0, it's probably my easiest number to plug in. I get 1 plus e to the 0, that's 2. Any real number to the 0 power is 1, except for 0. Now, if you plug in -1, you get 1 plus 1 over e. I'm going to approximate that. And here you're going to get 1 plus e. So what are these values approximately? Well, I used a calculator ahead of time. So this is about 1.37. And this one is about 3.7. So the coordinates you get from this are negative 1, 1.37, 0, 2, and 1, 3.7. So I'm going to take these, and I'm going to graph them over here. So I'll graph negative 1, and then I'll come up here to about 1.37. We'll just like eyeball it. It'll be like here. Next, I'm going to need 0, 2, so that's right here. And then finally, I'll need 1, 3.7, so we'll say that's like about up here. So you want to read graphs from left to right to determine if they're increasing or decreasing. If you think about it, no matter what you plug into the e of x function, it's going to be greater than 0 for all real x values. So no matter how large of a negative number or how large a positive number, you're always going to have that this is true. So the graph kind of approaches 1, but never quite gets there. So this is what the graph looks like. You call this a horizontal asymptote. That might ring a bell for some of you. This is called a horizontal asymptote. We would say it's at y equals 1, because that's a horizontal line. So examining this graph, if you were, I don't know, riding a bike, and this was some kind of ramp, you'd start on the left, and would you be going up or down, or would you be pedaling uphill or downhill? Well, you would start to struggle right here because you're pedaling uphill. So f of x, in this case, is increasing for all real x. And that's just the visual that I see here. That's what this definition here means, just graphically. So you're going up, reading left to right. If I can just draw a quick little sketch here. This is just some random graph. Again, you would read it left to right. From here until I hit this kind of like peak, this is an increasing interval. But then I can chop it up, and then suddenly if I'm riding my bike, I don't have to pedal so hard because I'm going downhill. So from here to this valley here, this is decreasing. And you can keep chopping up continuous graphs like this into their decreasing and increasing parts. So that's what we mean by increasing and decreasing. OK, I hope this was a good review of increasing. We have a new type of graph, exponential. They look like this J kind of thing. From here, we're going to review trig functions, the dreaded unit circle, just lots of stuff from trigonometry. So I'll see you soon. All right, so let's begin our trig review. So typically in calculus, angles are measured in radians. That's not to say that we won't sometimes use degrees. In fact, I kind of freely go back and forth between the two. But you will need to know kind of how to deal with both. So recall that radians measure the arc length counterclockwise along the unit circle. So if I just get a little sketch going here, I'll put it right over here so it's out of the way. The unit circle has radius 1, and you start your angle measure right here at the x-axis down here on the right side, and you begin moving counterclockwise like this. So that is the direction that an angle is measured in. And one full rotation counterclockwise is 2 pi radians, or also known as 360 degrees. So to get any other radian measure or degree measure, all you would need to do, I'm like hiding behind a text here, all you would need to do is chop this up. So for example, if I started from the beginning here and rotated halfway, a half rotation is how many radians would that be? If I chopped the 2 pi in half, it would be pi radians. And this is also known as, well, what if you did half of a circle, like half a rotation, it'd be 180 degrees. So all the degree measures, all the radian measures can be thought of as just taking pieces of the full 360 or the full 2 pi. You will need to know sine, cosine, tangent, like all those trig functions. They come back to haunt you in this class. You need to know them very well, actually. So let's review just some right triangle basics. So if we have a right triangle here, it's a right triangle because I drew that box, not because I'm a good artist or anything, but you have to believe me now, because I put that. Let's say that this theta is the measure of the angle right here, and we'll say x is the distance of the base, like how long the base is, and y is the height. Then, by the Pythagorean theorem, this is equal to the square root of x squared plus y squared. So that's how you find this longest side. So that's called the hypotenuse. So if I'm using terminology here, this side is called the adjacent. Adjacent just means next to, like in English. It's next to the angle. This side is called the opposite. And that's just because it's, if you have the angle here, it's opposite the angle. You have to go across to get there. And like I said, this one across from the right angle, this is the longest side, and it's called the hypotenuse. So that's like the terminology for those. Now we define the trig functions by just picking two sides here. So for example, if you want sine of theta, so you have to give me an angle to start with. If you want sine of theta, you go opposite and then hypotenuse. So this one is opposite over hypotenuse. For cosine, you go adjacent over hypotenuse. And then for tangent, this one, you actually do opposite over adjacent. So this one is opposite over adjacent, just like that. And notice these are, I just called like opposite as y, for example. You could just plug in y for opposite. Or for hypotenuse here, you could plug in the expression I have here, square root of x squared plus y squared. You could put that in here instead. But I'm just calling them their English word names. There are lots of trig identities, and there are a smaller set of those that will be very useful for this class. I picked out the ones that I think are the most useful. So these are the ones I really think you should commit to memory. This is just going to help you so much. So important trig identities. So I would make a note of these if you don't already know these. So sine squared of an angle plus cosine squared is 1. Tangent squared plus 1 is secant squared. And 1 plus cotangent squared is cosecant squared. These are called the Pythagorean identities. If you ever need to look them up on Google or something, they're called the Pythagorean identities. Along with these, it's good to know that sine is an odd function. What that means is that if you plug in a negative value here, the negative just escapes out front, and that's equal to the same thing. So you can just bring the negative out front. In contrast, did I say this was even? I said this is odd. I'm going to write it. Sine is an odd function. I honestly don't remember what I just said. So sine is an odd function. Cosine here is called an even function. If I write it, you should believe that. So what this means is that if you plug in a negative value, it just never happened. It just disappears. And those are equal to the same thing. Less important, but could be useful, is also things like this. So if you have cosecant, that's equal to 1 over sine of x. So what I'm going to write now are called the reciprocal identities. Similarly, the other ones are secant is 1 over cosine, and cotangent is 1 over tangent. So you flip the respective function to get the reciprocal identity. So these are the most important ones that I think you should be aware of. In the next part of this video, I think we're going to actually start evaluating these trig functions at unit circle measures. So we're going to remind you of how to do that. So I'll see you then. Let's go over some of the basic unit circle review that you're going to need for this class. So in the upper left here, I have the basic trig functions as well as what their values are at different angle measures. So I would expect you to know this as a minimum coming into this class because you're going to be using this later throughout the entire class to solve equations, and you don't want to get hung up on small details like this to finish a problem. The way you read this is like this. So if you have an angle measure 0, for example, sine of 0 is 0, cosine of 0 degrees is 1, and tangent is the first row divided by the second row. So remember, tangent is sine divided by cosine. So to get anything in this third row, you just take the first row and divide it by the second. It's worth noting that 1 divided by 0 here is undefined. So tangent is not defined at pi over 2. And if I just read another one for you, sine of pi over 4, if you read that, that's root 2 over 2. So again, these are the basic ones that I want you to have down very, very well. And I'm going to show you now the relationship of taking these and moving them into different quadrants. So I'm going to show you that in just a moment. So these angle measures here are the important ones. Starting from 0, you have pi over 6 is next. So what I'm going to do is I'm going to draw this out for you. So let's draw this together. Here we're looking in quadrant 1. 0 degrees is right here on the x-axis. And then if I rotate 30 degrees up like this is considered the positive direction if I'm going counterclockwise. This is 30 degrees, and the radian measure for that is pi over 6. 45 degrees is here, and it's halfway between the x-axis and the y-axis, so this is pi over 4. Right here at 60 degrees from the x-axis, this is pi over 3. And then finally, if you're vertical here, so from here, you make a 90-degree angle, this is pi over 2. So 90 degrees is considered pi over 2. Now we define x and y to be the sine or cosine of the angle on the unit circle. So cosine of the angle on the unit circle is the x-coordinate, and y is the sine of the angle on the unit circle. So this is a very important point to make. And then the last key ingredient we need is to know what sign we are in each quadrant, and that's SIGN, not SIN. So quadrant 1 starts here in the upper right. Your x-coordinate is positive here, and your y-coordinate is positive here. And we rotate counterclockwise, just like we do with the angles. So in quadrant 2 here, you have a negative for the x-coordinate and a positive for the y-coordinate because you go left and then up to have a point in that quadrant. Quadrant 3, you have both of x and y are negative because you go left and down from the origin. And then quadrant 4 is down here, and this is positive and negative. So x is positive because you go to the right, and y is negative because you go down. So all of these pieces together help you efficiently find the values of sine, cosine, and tangent for most angles. So here we have 30 degrees here. So what I'm looking for here is the point on the unit circle at 30 degrees. So to do this, what I would need to do is go to the 30-degree column here. And the cosine is the x-coordinate. So cosine is x-coordinate. So cosine is root 3 over 2. And then this sine is the y-coordinate, which is 1/2. So the specific point on the unit circle at 30 degrees is root 3 over 2, 1/2. And this continues for all of these angles here. So I just wanted to show you one example of that. They're both positive because 30 degrees is still in the first quadrant. Let's take a look at these examples to get some more practice at this. So first one's pi over 6. I'm just going to draw where that is first. So we know pi over 6 is right here. So what this is asking you, and I started with an easy example because we've already talked about this, sine is asking you for the y-coordinate. That's what sine is. And you want the y-coordinate at pi over 6, which is 30 degrees. So if you have a solid understanding of your unit circle measures, you know that this point right here is square root of 3 over 2, comma 1/2. And then the y-coordinate you're looking for, that's 1/2 right here. And if I go over to my table, I have pi over 6, 1/2 is sine. So this answer is positive because we're still in the first quadrant and the y-coordinate is positive. So all the things are lining up here. Let's do a different example now of an angle we haven't looked at just yet. So first thing I'm going to do is I'm going to draw where this is. So 3 pi over 4. Well, I'm going to start with pi over 4 because that's the unit circle measure I know the best. So this is pi over 4. That's at 45 degrees. I know that this is root 2 over 2 comma root 2 over 2 because that is one of my basic unit circle measures here. Problem is I don't want pi over 4, I want 3 pi over 4. So I need to just move this to the correct spot. 45 degrees is 1 pi over 4. I need 3 of them, so if I move to 2 pi over 4, so 45 plus 45, I'm here at 90 degrees. But I need a third one, so another 45 degrees would put me where? It's at 135 degrees. So this right here is 3 pi over 4, which is 135 degrees. So we're looking at this point here, this root 2 over 2, root 2 over 2. Cosine is the x-coordinate. So we're really going to focus on the x-coordinate here, root 2 over 2. And we're in quadrant 2 now. So in quadrant 2, the x-coordinate is negative. So I'm going to take this exact same number, and I'm just going to make it negative. So here I have negative root 2 over 2, root 2 over 2. The y is positive, so this y will be positive. But my answer here, the x-coordinate is this one, which is negative root 2 over 2. There's a lot of things you need to be checking as you're doing these kinds of problems, making sure if you're in the correct quadrant, does your sign, the sign of the answer match where you are. Make sure if you have the beginning angle here that you've moved to the correct quadrant. So you can always use one of these starting angles here to move yourself to the correct quadrant. OK, so I hope that helped you. You should practice many more examples. So just change this angle measure and see if you can do the same thing I just did. I'm going to move on now. So we're going to solve an equation. And in one of the very last steps, we're going to have to do this sort of thing to find the answers. So this combines solving equations from the previous lecture and this new stuff. So to solve this equation, I should look for what's in common with these two terms. And the thing in common is cosine x. I'm going to draw a giant bracket there. And then what's left here? Well, I have 2 cosine is left. Minus, I've removed the 1 cosine here, put it in front. So root 3 is the only thing left in that term. I have this factor times this factor is 0. So I can split this up into 2 smaller problems. So either cosine of x is 0, or 2 cosine of x minus 3 is 0. Now this is asking the question, where is the x-coordinate 0 on the unit circle? So if we take a look at the unit circle here, or I could look up here, that gives me one of them. But if I'm here at 90 degrees, the point is 0, 1. So 90 degrees, the point is 0, 1. X is the cosine, which is what I'm looking for here. So I'm focusing on the x-coordinate because we're talking about cosine. and at this specific spot, the x is 0. So one of these answers is 90 degrees. So that would be pi over 2. I've written this as degrees, so I'm gonna stick with degrees here. So this is going to be 90 degrees. Is there another spot on this interval right here from 0 to 360 degrees where the x-coordinate is 0? There is another one. So if you keep going around, this point down here at 270 degrees, or 3 pi over 2s, the point is 0, -1. But the important thing is that this first coordinate, cosine, is 0. So 270 degrees is another spot where this is true. How about here? So first I'm going to isolate the trig part. So I'm going to add root 3, and I'm going to divide by 2. So cosine of x is root 3 over 2. And over here, I'm going to draw a picture to kind of help me see what's going on. If we know the first quadrant really well, so if we know that basic table really well, we should know which angle here has root 3 over 2 for cosine. So that's going to be pi over 6. So at pi over 6, or 30 degrees, the coordinate here is root 3 over 2, comma a half. This is the one I'm interested in because the x-coordinate is root 3 over 2, and cosine is the x-coordinate. So they're both root 3 over 2. So this is one of my answers. So this is 30 degrees. This is positive root 3 over 2. So I need the other quadrant where the x-coordinate stays positive. That goes back to this right here. So which other quadrant has the x-coordinate positive? It's this one. So I need to make sure that my other angle is in this quadrant. So I'm going to take the mirror image, just like this. So this is the point, root 3 over 2, because we went to the right. And now we've gone down to -1/2. But that doesn't matter, because cosine's only focusing on the x-coordinate here. So if we've gone 30 degrees positive this way, the mirror image is 30 degrees this way. What angle measure do you get when you take a full rotation, 360, and you subtract 30 going this way? That's going to be 330 degrees, which is my other solution. So we found both angles where cosine is positive root 3 over 2. It's here and also in the fourth quadrant here. Thank you so much for watching. Please try your lecture quiz and contact me if you have any questions. See you next time. Bye.